Hello, hi everyone. Assalamualaikum warahmatullahi wabarakatuh and good day to all of you. So now we will continue our topic 4 in this subject, numerical solution of ordinary differential equation with subtopic 4.2, which is Runge-Kutta method. The Runge-Kutta methods achieve the accuracy of a Taylor series approach without requiring the calculation of higher derivatives. So many variations exist, but all can be cast in the general form of this yi plus 1 equal to yi plus a function of phi with xi, yi and h multiplied by h. So h here is the step size for the calculation, and the function of phi, as in the red bracket, is actually an increment function that represents slope over the interval. So this increment function can be written in the general form of phi equal to a1 k1 plus a2 k2 plus so on until an kn, where a's are constant and the k's are as given in this set of equations. Okay, so p's and q's in this set of equations is actually a constant. Okay, p1 and q11 and so on. That we can see that k's are recurrence relationship. For example, you can see that k1 appears in the k2 equation, and both k1 and k2 appears in the k3 equations, and so on until kn. So there are various types of Runge-Kutta methods that can be devised by employing different numbers of terms in the increment function as specified by n. So you can see here that the first order of Archi method with n equal to 1 is actually an Euler's method. Okay, for this Runge-Kutta method, we will look closely on two versions of the method, which is first is the second order method, and the second one is the fourth order of Runge-Kutta method. Okay, so for the second order version, the general form of the equations is equal to yi plus 1 equal to yi plus in bracket a1 k1 plus a2 k2 multiplied by h. Okay, where h is the step of the size of the step. So k1 here is the function of xi and yi, and k2 is the function of xi plus p1 h and yi plus q11 k1 h. Okay, so the values for a1, a2 and p1 and q11, or the constants of the equations, can be evaluated by setting the equation, the general equation here, equal to a Taylor series expansion to the second order term. So by doing this, it can be three equations can be derived to evaluate the four unknown constants. So the equations are here. Okay, a1 plus a2 equal to 1, a2 p1 equal to 1 over 2, and a2 q11 equal to 1 over 2. Notice here, because we have three equations, we only have three equations with four unknowns. So we need to assume a value of one of the unknowns to determine the other three. For example, if we assume value of a2, okay, then we can get the other unknown's value by solving the simultaneous equation. Alright. Because we can choose an infinite number of a2, because a2 is an assumption, so there will be an infinite number of second order Archi methods. So every versions would yield exactly the same result if the solution of the ODE were quadratic, linear, or a constant. But it can yield different results where the solution is more complicated. Okay, so the most commonly used and from a famous method is shown after this. Okay, so these three are the most commonly used to determine value of A2 or to assume value of A2 and determine the other three constant values. So the first one is the Hune method, where A2 is assumed to be 1 over 2, thus making A1 equal to 1 over 2 and P1 equal to Q1 equal to 1. So these constant values will yield the general equation of yi plus 1 equal to yi plus in bracket half k1 plus half k2 multiplied by h. And then the second one is the midpoint method, where A2 is assumed to be 1. Thus solving the A1 equal to 0 and P1 Q11 equal to 1 over 2. So this constant value will yield the general form of the equations yi plus 1 equal to yi plus by k2h. Okay, and the last one is the Ralston method, where A2 is assumed to be 2 over 3. Thus from there we can obtain the value for A1 and P1 Q11, where A1 equal to 1 over 3 and P1 equal to Q11 equal to 3 over 4. So these constant values will bring the general form to be equal to yi plus 1 equal to yi plus in bracket 1/3 of k1 plus 2/3 of k2h. Okay, now we look at the example 5 from the lecture notes. It's about comparison of various second order of RUNGE-KUTTA schemes. So the question is, use the midpoint method and Ralston method to numerically integrate the function of xy equal to negative 2x cubed plus 12x squared minus 20x plus 8.5. So from x equal to 0 to x equal to 4 using the step size of 0.5. The initial conditions is at x equal to 0 is y equal to 1. And compare the result with the values obtained using another second order RUNGE-KUTTA algorithm, which is Hune method. So for the solution, for A is the exact solution, where you can directly integrate the function of x and y. So from there you can get the integration will get to negative 0.5 x power 4 plus 4x cubed minus 10x squared plus 8.5 x plus c. So when you have c in the equation, this is where the initial condition is useful. Okay, by applying the initial condition of x equal to 0 and y equal to 1, we can get the value of c equal to 1. Okay, so now for x equal to 0.5, the y function is equal to 3.21875. Okay, right. So for the other two methods, which are midpoint method and Ralston method, the calculation can be done based on the set of equations given previously or in the lecture notes. So here we get y1 by using midpoint method is equal to 3.109375. This yield to the true error equal to 3.4%. Comparing to Ralston method, the y1 value is 3.27734 and yielding the true error equal to 1.89%. And the last method, which is Hune method, the y1 obtained is 3.4375 with the true error of 6.8%, which is the highest among the three methods. And then the computation is repeated and the result will be summarized in the next figure and table. Okay, table 4 here shown a comparison of true and approximate values of y from the example 5 with the initial condition at x equal to 0 when y equal to 1. So this is the initial condition. And then the approximate values were computed using 3 versions of second order RUNGE method, that are Yun, midpoint, and Ralston method. While for figure 14 is the comparison of two solutions using 3 second order RUNGE-KUTTA method and Euler method. So notice how all the second order methods, which is here, are superior to the Euler's method. So we can see that the Euler's method is quite far from the other three method. Alright. Okay, so now we will look at the fourth order of RUNGE-KUTTA method. Okay, this method is actually the most popular of the RUNGE method, as with the second approaches there are infinite number of versions. So the following is the most commonly used form, and it called as the classical fourth order of RUNGE-KUTTA method. So the general form of the fourth order RUNGE-KUTTA method is yi plus 1 equal to yi plus 1 over 6 in bracket or multiply by k1 plus 2 k2 plus 2 k3 plus k4 multiplied by h, or the step size. Okay, notice that for ODEs that a function of x alone, the classical fourth order RUNGE method is similar to the Yun approach. Alright, and as depicted in figure 15, okay, each k of the, okay, each k here, k1, k2, k3, and k4, it's representing a slope from, you can see from figure 15. So each of k is actually a slope. Then the general equation here represent a weighted average of these slopes to arrive at the improved slope, which is the summation of k1, k2, k3, and k4 multiplied by 1 over 6. Okay. Alright, for a better understanding in the fourth order RUNGE method, let us look at example 7. So for this example, use the classical fourth order RUNGE method to integrate the function of xy equal to 4e power 0.8x minus 0.5y. By using h equal to 0.5 and the initial condition of y 0 equal to 2 from x 0 to 0.5. So this is the initial function, and this is the step size, and this is the range of the integration. Okay, so for the solution, by using fourth order RUNGE method, the slope at the beginning of the interval is computed as k1. Okay, k1 is equal to the function of x naught and y naught, which this is when you use the initial function, initial condition of y0 equal to 2. So we get k1 equal to 3. And then this value is used to compute a slope at a midpoint, k2. So here, after doing the calculation, we will get k2 equal to 3.510611. So this slope, or the k2 slope, in turn is used to compute another slope at the midpoint, which is k3. Okay, so notice here we have k2 in the k3 equation. So after doing the calculation, we will get k3 equal to 3.446785. Next, this slope of k3 is used to compute a slope at the end of the interval, which is k4. So k4 from this calculation is equal to 4.105603. So finally, the four slope estimates are combined to yield an average slope. So this average slope is then used to make the final prediction at the end of the interval. So this is the final prediction of y1. Okay, after conducting the calculation, we will get y1 equal to 3.751699, which if we compare with the true solution, so it's actually close to the true solution. Okay. Okay, last but not least, please do the exercise 1 for the whole topic of topic 4. So the question is, solve the following initial value problem over the interval from t equal to 0 to 2, where y when x equal to 0 is 1. So display all your results in the same graph. Okay, given the dy dt is equal to y t square minus 1.1y. So you need to do it as analytically, and then the second one, Euler's method, midpoint method, and fourth order method. So I wish you all the best.